The memory hierarchy. Today's storage technologies and trends. Locality of reference. Let it wash over you. Locality of reference. Caching in the memory hierarchy. Main memory equals DRAM. Random access memory, RAM. Key features. RAM is traditionally packaged as a chip. Basic storage unit is normally a cell, 1 bit per cell. Multiple RAM chips form a memory. Static RAM, SRAM. Each cell stores a bit with a 4 or 6 transistor circuit. Retains value indefinitely, as long as it is kept powered. Relatively insensitive to electrical noise, EMI, radiation, etc. Faster and more expensive than DRAM. Dynamic RAM, DRAM. Each cell stores bit with a capacitor. 1 transistor is used for access. Value must be refreshed every 10 to 100 ms. More sensitive to disturbances, EMI, radiation, than SRAM. Slower and cheaper than SRAM. SRAM versus DRAM. Summary trends. Access needs. Per bit time refresh, EDC, cost. Applications. SRAM 4 or 6 1x, no maybe 100x cache memories. DRAM 110x yes 1x main memories. Frame buffers. The memory bottleneck. Typical CPU clock rate. Typical DRAM access time. 1 GHz, 1 ns cycle time. Typical DRAM access time. 30 ns, about 30 cycles. Typical main memory access. 100 ns, 100 cycles. DRAM, 30, pre-charge, 10, chip crossings, 30, overhead, 30. Our pipeline designs assume 1 cycle access, 1 ns. Average instruction references. 1 instruction word. 0.3 data words. This problem gets worse. CPUs get faster. Memories get bigger. Memory delay is mostly communication time. Reading/writing a bit is fast. It takes time to select the right bit. Route the data to / from the bit. Big memories are slow. Small memories can be made fast. Lecture 14. Conventional DRAM organization. DXW DRAM. DW total bits organized as D supercells of size W bits. 16 by 8 DRAM chip. Calls 1, 2, 3. Memory. Controller. 2 bits. / address. 1. Rows. 2. Supercell. 2, 1. To / from CPU. 3. 8 bits. / data. Internal row buffer. Reading DRAM supercell, 2, 1. Step 1a, row access strobe, RAS, selects row 2. Step 1b, row 2 copied from DRAM array to row buffer. 16 by 8 DRAM chip. Calls. Memory. Controller. 1, 2, 3. RAS equals 2. 2. / address. 1. Rows. 2, 3. 8. / data. Internal row buffer. Reading DRAM supercell, 2, 1. Step 2a, column access strobe, CAS, selects column 1. Step 2b, supercell, 2, 1, copied from buffer to data lines, and eventually back to the CPU. 16 by 8 DRAM chip. Calls. Memory. Controller. 1. 2, 3. Cas equals 1, 2, slash. Address. Supercell. 2, 1. To CPU. 1. Rows. 2, 3. 8. Slash. Data. Supercell. 2, 1. Internal row buffer. DRAM access time. RAS. Cas. Address. Row. Column. Doubt. Data valid. Lecture 17. 64-bit double word at main memory address A. Memory modules. Address, row equals I, col equals J. Supercell, I, J. DRAM 0. 64 megabytes. Memory module. Consisting of 8 8mx8 DRAMs. 31. 7. 8. 15. 16. 23. 24. 32. 63. 39. 40. 47. 48. 55. 56. 64-bit double word at main memory address A. Bits. 0 to 7. 8 to 15. 16 to 23. 24 to 31. 32 to 39. 40 to 47. 48 to 55. 56 to 63. DRAM 7. 64-bit double word. 31. 7. 8. 15. 16. 23. 24. 32. 63. 39. 40. 47. 48. 55. 56. Memory. Controller, enhanced DRAMs. Basic DRAM cell has not changed since its invention in 1966. Commercialized by Intel in 1970. DRAM cores with better interface logic and faster I/O. Synchronous DRAM, SDRAM. Uses a conventional clock signal instead of asynchronous control. Allows reuse of the row addresses, for example, RAS, CAS, CAS, CAS. Double data rate synchronous DRAM, DDR/SDRAM. Double edge clocking sends 2 bits per cycle per pin. Each generation incompatible, DDR, DDR2, DDR3, soon DDR4. Nearly doubles data rate, by increasing internal clock rate. Reduces power. By 2012, DDR3 standard for most server and desktop systems. Intel Core i7 supports only DDR3 SDRAM, better memory system performance. Bandwidth versus latency. Bandwidth equals #bits transferred per cycle. Latency equals time to access DRAM. Bandwidth. Memory bus width, 16, 32, 64. Multiple memory banks. Address interleaving. Multiple memory controllers, independent. Latency. Synchronous DRAM access modes. Faster interface, RAM bus. Lecture 17. Non-volatile memories. DRAM and SRAM are volatile memories. Lose information if powered off. Non-volatile memories retain value even if powered off. Read-only memory, ROM, programmed during production. Programmable ROM, PROM, can be programmed once. Erasable PROM, EPROM, can be bulk erased, UV, X-ray. Electrically erasable PROM, EPROM, electronic erase capability. Flash memory, EPROMs with partial, sector, erase capability. Wears out after about 100,000 erasings. Uses for non-volatile memories. Firmware programs stored in a ROM, BIOS, controllers for disks, network cards, graphics accelerators, security subsystems. Solid-state disks, replace rotating disks in thumb drives, smartphones, MP3 players, tablets, laptops. Disk caches. Traditional bus structure connecting CPU and memory. A bus is a collection of parallel wires that carry address, data, and control signals. Buses are typically shared by multiple devices. CPU chip. Register file. ALU. System bus. Memory bus. Main. Memory. Bus interface. I/O. Bridge, memory read transaction, 1. CPU places address A on the memory bus. Register file. Load operation, move lay, %x. ALU. %x. Main memory. I/O bridge. A. Bus interface. A. X. Memory read transaction, 2. Main memory reads A from the memory bus, retrieves word X, and places it on the bus. Register file. ALU. Load operation, move lay, %x. %x. Main memory. I/O bridge. X. Bus interface. A. X. Memory read transaction, 3. CPU read word X from the bus and copies it into register %x. Register file. Load operation, move lay, %x. ALU. %x. X. Main memory. I/O bridge. Bus interface. A. X. Memory write transaction, 1. CPU places address A on bus. Main memory reads it and waits for the corresponding data word to arrive. Register file. Store operation, move %x, A. ALU. %x. Y. Main memory. I/O bridge. A. Bus interface. A. Memory write transaction, 2. CPU places data word Y on the bus. Register file. Store operation, move %x, A. ALU. %x. Y. Main memory. I/O bridge. Y. Bus interface. A. Memory write transaction, 3. Main memory reads data word Y from the bus and stores it at address A. Register file. ALU. Store operation, move %x, A. %x. Y. Main memory. I/O bridge. Bus interface. A. Y. What's inside a disk drive? Spindle. Arm. Platters. Actuator. Electronics. Including A. Processor. And memory. SCSI. Connector. Image courtesy of Seagate Technology. Disk geometry. Disks consist of platters, each with 2 surfaces. Each surface consists of concentric rings called tracks. Each track consists of sectors separated by gaps. Spindle. Surface. Tracks. Track K. Sectors. Gaps. Disk geometry, multiple platter view. Aligned tracks form a cylinder. Cylinder K. Surface 0. Platter 0. Surface 1. Surface 2. Platter 1. Surface 3. Surface 4. Platter 2. Surface 5. Spindle. Disk capacity, maximum number of bits that can be stored. Vendors express capacity in units of gigabytes, GB, where 1 gigabyte equals 109 bytes, lawsuit pending. Claims deceptive advertising. Capacity is determined by these technology factors. Recording density, bits/in, number of bits that can be squeezed into a 1-inch segment of a track. Track density, tracks/in, number of tracks that can be squeezed into a 1-inch radial segment. Areal density, bits/in2, product of recording and track density. Modern disks partition tracks into disjoint subsets called recording zones. Each track in a zone has the same number of sectors, determined by the circumference of innermost track. Each zone has a different number of sectors/track. Computing disk capacity. Capacity equals hash bytes/sector, x, average hash sectors/track, x. Hash tracks/surface, x, hash surfaces/platter, x. Hash platters/disk. Example: 512 bytes/sector. 300 sectors/track, on average. 20,000 tracks/surface. 2 surfaces/platter. 5 platters/disk. Capacity equals 512 by 300 by 20,000 by 2 by 5. Equals 30,720,000,000. Equals 30.72 gigabytes. Disk operation, single platter view. The disk surface spins at a fixed rotational rate. By moving radially, the arm can position the read/write head over any track. The read/write head is attached to the end of the arm and flies over the disk surface on a thin cushion of air. Spindle. 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 Disk operation, multi-platter view. Read/write heads move in unison from cylinder to cylinder. Arm. Spindle. Disk structure, top view of single platter. Surface organized into tracks. Tracks divided into sectors. Goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access head in position above a track goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access rotation is counterclockwise goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, read about to read blue sector goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, read after reading blue sector after blue read goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, read read request scheduled next after blue read goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, seek to read track after blue read seek for red. Goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, rotational latency. After blue read. Seek for red. Rotational latency. Wait for red sector to rotate around. Goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, read complete read of red after blue read seek for red. Rotational latency. After red read. Complete read of red. Goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Disk access, service time components. After blue read. Seek for red. Rotational latency. After red read. Goal. Show the inefficiency of current disk requests. Conveyed ideas. Rotational latency is wasted time that can be used to service tasks. Background information. None. Slide background. Kill text and arrows. Data transfer. Seek. Rotational. Latency. Data transfer. Disk access time. Average time to access some target sector approximated by access equals TIVG seek plus TIVG rotation plus TIVG transfer. Seek time, TIVG seek. Time to position heads over cylinder containing target sector. Typical TIVG seek is 3.9 ms. Rotational latency, TIVG rotation. Time waiting for first bit of target sector to pass under RW head. TIVG rotation equals half x1/rpms x 60 seconds/1 minute. Typical TIVG rotation equals 7,200 rpms. Transfer time, TIVG transfer. Time to read the bits in the target sector. TIVG transfer equals 1/rpm x 1/average hash sectors/track, x 60 seconds/1 minute. Disk access time example. Given. Rotational rate equals 7,200 rpm. Average seek time equals 9 ms. Average hash sectors/track equals 400. Derived. TIVG rotation equals half x, 60 seconds/7200 rpm, x 1000 ms per second equals 4 ms. TIVG transfer equals 67,200 rpm x 1/400th of a seconds/track x 1000 ms per second equals 0.02 ms. Access equals 9 ms plus 4 ms plus 0.02 ms. Important points. Access time dominated by seek time and rotational latency. First bit in a sector is the most expensive, the rest are free. SRAM access time is about 4 ns/double word, DRAM about 60 in S. Disk is about 40,000 times slower than SRAM. 2,500 times slower than DRAM. Logical disk blocks. Modern disks present a simpler abstract view of the complex sector geometry. The set of available sectors is modeled as a sequence of B-sized logical blocks, 0, 1, 2. Mapping between logical blocks and actual, physical, sectors. Maintained by hardware/firmware device called disk controller. Converts requests for logical blocks into surface, track, sector, triples. Allows controller to set aside spare cylinders for each zone. Accounts for the difference in formatted capacity and maximum capacity. I/O bus CPU chip register file ALU system bus memory bus main memory. Bus interface. I/O. Bridge. I/O bus. Expansion slots for other devices such as network adapters. USB. Controller. Graphics. Adapter. Disk. Controller. Mouse. Keyboard. Monitor. Disk. Reading a disk sector, 1. CPU chip. CPU initiates a disk read by writing a command, logical block number, and destination memory address to a port, address, associated with disk controller. Register file. ALU. Main. Memory. Bus interface. I/O bus. USB. Controller. Graphics. Adapter. Disk. Controller. Keyboard. Mouse. Monitor. Disk. Reading a disk sector, 2. CPU chip. Disk controller reads the sector and performs a direct memory access, DMA, transfer into main memory. Register file. ALU. Main. Memory. Bus interface. I/O bus. USB. Controller. Graphics. Adapter. Disk. Controller. Mouse. Keyboard. Monitor. Disk. Reading a disk sector, 3. CPU chip. When the DMA transfer completes, the disk controller notifies the CPU with an interrupt, i.e., asserts a special interrupt pin on the CPU. Register file. ALU. Main. Memory. Bus interface. I/O bus. USB. Controller. Graphics. Adapter. Disk. Controller. Mouse. Keyboard. Monitor. Disk. Solid-state disks, SSDs. I/O bus. Requests to read and write logical disk blocks. Solid-state disk, SSD. Flash. Translation layer. Flash memory. Block 0. Block B1. Page 0. Page 1. Page P1. Page 0. Page 1. Page P1. Pages, 512 kilobytes to 4 kilobytes, blocks, 32 to 128 pages. Data read/written in units of pages. Page can be written only after its block has been erased. A block wears out after 100,000 repeated writes. SSD performance characteristics. Sequential read put 250 megabytes per second. Sequential write put 170 megabytes per second. Random read put 140 megabytes per second. Random write put 14 megabytes per second. Rand read access 30 US. Random write access 300 US. Why are random writes so slow? Erasing a block is slow, around 1 ms. Write to a page triggers a copy of all useful pages in the block. Find unused block, new block, and erase it. Write the page into the new block. Copy other pages from old block to the new block. SSD trade-offs versus rotating disks. Advantages: no moving parts, faster, less power, more rugged. Disadvantages: have the potential to wear out. Mitigated by wear leveling logic and flash translation layer. For example, Intel X25 guarantees 1 petabyte, 1015 bytes, of random writes before they wear out. In 2010, about 100 times more expensive per byte. Applications: MP3 players, smartphones, laptops. Beginning to appear in desktops and servers. Storage trends: metric 1980, 1985, 1990, 1995, 2000, 2005, 2010, 2010:1980. SRAM. Metric 1980, 1985, 1990, 1995, 2000, 2005, 2010, 2010:1980. $/MB 19,200 2,900 320 256 175 60 320. Access, NS, 300 150 35 15 32 1.5 200. DRAM. Metric 1980, 1985, 1990, 1995, 2000, 2005, 2010, 2010:1980. $/MB 8880 131 0.10 0.06 130,000. Access, NS, 375 200 170 60 50 49. Typical size, MB, 0.064 0.2564 1664 2000 8100 25,000. Disk. Metric 1980, 1985, 1990, 1995, 2000, 2005, 2010, 2010:1980. $/MB 500 108 0.300 0.010 0.005 0.00031 1,600,000. Access, MS, 8775 28 10 843 29. Typical size, MB, 110 161,000 20,000 160,000 1,500,000 1,500,000. CPU clock rates inflection point in computer history. When designers hit the power wall. 1980, 1990, 1995, 2000, 2003, 2005, 2010, 2010:1980. CPU 8080 386 Pentium P3 P4 Core 2 Core i7. Clock. Rate, MHz, 120, 150, 600, 3300 2000, 2500, 2500. Cycle. Time, NS, 1056 1.60 0.30 0.50 0.4 2500. Cores 11111244. Effective. Cycle 1056 1.60 0.30 0.25 0.1 10,000. Time, ns, the CPU memory gap. The gap widens between DRAM, disk, and CPU speeds. SSD, DRAM, CPU. The memory hierarchy registers L1 cache, L2 cache, DRAM disk tape. Latency, bandwidth, registers. 1 cyc 3 to 10 word/cycle compiler managed less than 1 kilobyte. 1 3 sci 1 to 2 word/cycle hardware managed 16 kilobytes minus 1 megabyte. 10 15 sci 1 to 2 word/cycle hardware managed 1 megabyte to 12 megabytes. 5300 sci 0.5 word/cycle OS managed 64 megabytes to 4 gigabytes. 106 107 sci 0.01 words/cycle OS managed 40 gigabytes plus. CPU. Chip. L1 cache. L2 cache. Chips. DRAM. Disk. Mechanical. Tape. Lecture 14. Locality to the rescue. The key to bridging this CPU memory gap is a fundamental property of computer programs known as locality. Today's storage technologies and trends. Locality of reference. Caching in the memory hierarchy. Locality. Principle of locality. Programs tend to use data and instructions with addresses near or equal to those they have used recently. Temporal locality. Recently referenced items are likely to be referenced again in the near future. Spatial locality. Items with nearby addresses tend to be referenced close together in time. Locality example. Data references. Spatial locality. Sum equals 0. For I equals 0, I less than n, I plus plus. Sum plus equals ai. Return sum. Data references. Reference array elements in succession, stride 1 reference pattern. Reference variable sum each iteration. Instruction references. Reference instructions in sequence. Cycle through loop repeatedly. Spatial locality. Temporal locality. Spatial locality. Temporal locality. Qualitative estimates of locality. Claim, being able to look at code and get a qualitative sense of its locality is a key skill for a professional programmer. Question, does this function have good locality with respect to array A? In sum array rows into mn. Int I, j, sum equals 0. For I equals 0. I less than m, I plus plus. For j equals 0, j less than n, j plus plus. Sum plus equals aij. Return sum. Locality example. Question, does this function have good locality with respect to array A? In sum array calls into mn. Int I, j, sum equals 0. For j equals 0, j less than n, j plus plus. For I equals 0, I less than m, I plus plus. Sum plus equals aij. Return sum. Locality example. Question, can you permute the loops so that the function scans the 3D array A with a stride 1 reference pattern, and thus has good spatial locality? In sum array 3D into mnn. Int I, j, k, sum equals 0. For I equals 0, I less than m, I plus plus. For j equals 0, j less than n, j plus plus. For k equals 0, k less than n, k plus plus. Sum plus equals a kij. Return sum. Memory hierarchies. Some fundamental and enduring properties of hardware and software. Fast storage technologies cost more per byte, have less capacity, and require more power, heat. The gap between CPU and main memory speed is widening. Well-written programs tend to exhibit good locality. These fundamental properties complement each other beautifully. They suggest an approach for organizing memory and storage systems known as a memory hierarchy. Today's storage technologies and trends. Locality of reference. Caching in the memory hierarchy. An example memory hierarchy. CPU registers hold words retrieved from L1 cache. Registers. L1. L1 cache. SRAM. Smaller. Faster. Costlier. Per byte. L1 cache holds cache lines retrieved from L2 cache. L2. L2 cache. SRAM. L2 cache holds cache lines retrieved from main memory. L3. Main memory. DRAM. Larger. Slower. Cheaper. Per byte. Main memory holds disk blocks retrieved from local disks. L4. Local secondary storage. Local disks. Local disks hold files retrieved from disks on remote network servers. Remote secondary storage. Tapes, distributed file systems, web servers. L5. Caches. Cache, a smaller, faster storage device that acts as a staging area for a subset of the data in a larger, slower device. Fundamental idea of a memory hierarchy. For each K, the faster, smaller device at level K serves as a cache for the larger, slower device at level K+1. Why do memory hierarchies work? Because of locality, programs tend to access the data at level K more often than they access the data at level K+1. Thus, the storage at level K+1 can be slower, and thus larger and cheaper per bit. Big idea. The memory hierarchy creates a large pool of storage that costs as much as the cheap storage near the bottom, but that serves data to programs at the rate of the fast storage near the top. General cache concepts. Smaller, faster, more expensive. Memory cache is a subset of the blocks. Cache 8, 4, 9, 14. 10. 3. Data is copied in block size transfer units. 4. 10. Larger, slower, cheaper memory. Viewed as partitioned into blocks. Memory. 1. 2. 3. 4. 4. 5. 6. 7. 8. 9, 10, 10, 11, 12, 13, 14, 15. General cache concepts, hit. Request, 14. Data in block B is needed. Block B is in cache. Hit. Cache. 8. 9. 14. 14. 3. Memory. 1. 2. 3. 4. 5. 6. 7. 8. 9. 10. 11. 12. 13. 14. 15. General cache concepts, miss. Request, 12. Data in block B is needed. Block B is not in cache. Miss. Cache. 8. 9. 12. 14. 3. Block B is fetched from memory. 12. Request, 12. Block B is stored in cache. Placement policy determines where B goes. Replacement policy determines which block gets evicted, victim. Memory 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15. General caching concepts, types of cache misses. Cold, compulsory, miss. Cold misses occur because the line has never been touched. A cache whose size equals memory takes only cold misses. Conflict miss. Conflict misses occur when the level K cache is large enough, but multiple data objects all map to the same level K block. Arises from limited associativity and non-optimal replacement. Misses absent in a fully associative, optimal replacement policy cache are conflict misses. Capacity miss occurs when the set of active cache blocks, working set, is larger than the cache. Examples of caching in the hierarchy. Cache type. What is cached? Where is it cached? Latency, cycles. Managed by. Registers. 4 to 8 bytes words. CPU core. Compiler. TLB. Address translations. On-chip TLB. Hardware. L1 cache. 64 bytes block. On-chip L1. 1. Hardware. L2 cache. 64 bytes block. On/off chip L2. 10. Hardware. Virtual memory. 4 kilobyte page. Main memory. 100. Hardware plus OS. Buffer cache. Parts of files. Main memory. 100. OS. Disk cache. Disk sectors. Disk controller. 100,000. Disk firmware. Network buffer cache. Parts of files. Local disk. 10 million. AFS/NFS client. Browser cache. Web pages. Local disk. 10 million. Web browser. Web cache. Web pages. Remote server disks. 1 billion. Web proxy server.